temperature is rising here, visualized with warming stripes. And yeah, new temperature records being set every year. And yeah, one tool that's used in the assessment of climate change are also simple climate models, not only the bigger models. So these simple climate models, they can run much faster than the large and complex global circulation models. They can thus be used in policy analysis and also in economic models and for uncertainty analysis, and they can also be used to emulate these larger models. And the most widely used model is called MAGIC. It's a reduced complexity models, but unfortunately it's only publicly available as a Windows binary. And there was only a wrapper in MATLAB. It's using custom input and output formats, text-based formats, and the parameters need to be set as Fortran nameless. And this is of course not very nice, so I wrote a Python wrapper, PyMagic. And yeah, once you have it with a few lines of Python code, you can easily run a few scenarios and then plot them. And to give you a bit more of an insight what you can do with PyMagic, so you import it, then you import a couple of scenarios, so we can have a look what such a scenario looks like. So it's just a pandas data frame, which the different greenhouse gases in each column. And then we can plot the scenario. So this is what this RCP6 scenario looks like. Emissions are continue to rise until 2080, and then they start to decline. So this is only CO2 emissions from fossil fuel, but for this example, I only stick to this. And since it's just the scenario is just stored as a pandas data frame, I can. Oh, sorry. First, we can run the scenario and look what temperature this gives us at the end of the century. So this is 3.2 degrees above the pre-industrial period, here defined as 1850 to 1900. And yeah, now I want to have a look what I can do with a different scenario. So I make a copy and start to modify it. And I say, let's start reducing CO2 emissions right in 2020. So with pandas interpolate function, this is quite easy. And now I have a scenario where emissions decline from 2020. And I can plot these two together. So this is what's in red is the default scenario, and in blue dashed is my new test scenario. All other greenhouse gases kept at the same as in the original RCP scenario. And then I can run this again, and I get 2.1 degrees. So by reducing CO2 emissions, we've avoided about 1 degree of warming. So this is only a toy example, of course, but I hope it gives you an idea what you can do with PyMagic. So PyMagic is now also being used to drive the continuous development of the core magic model written in Fortran. So to test it and to drive the continuous integration. We also wrote this up for the Journal of Open Source Software for JOS, which was a nice process to have an open peer review process on GitHub. So I can only recommend publishing there if you have your own scientific software tools. And yeah, due to Magic not being publicly available as open source, a number of other simple climate models have been developed. One is Hector, developed at the Joint Global Change Research Institute. It's written in C++. Was also hard to use, so you had to write ini files and yeah, command line runs. And together with my colleagues von Wilner, we developed also a Python wrapper. So it's a direct Python interface into the C++ code, so it's quite fast. Also much faster than Magic, where there's a lot of copying around of files and everything. And then there's the FAIR model, developed in Oxford and Leeds. And the nice thing about FAIR is that it's completely written in Python, so it's quite easy to dive into the code and try to figure out what's going on. So these PyMagic, PyHector, and FAIR are the yeah, models currently available in Python. So PyMagic and PyHector can easily be, well, so inputs and outputs are pandas data frames, so they're easy to write and read. Inputs and outputs. PyMagic is a bit slower because it uses Wine when it's not on Windows, so on Linux and Mac it's a bit slower. The Hector model is quite fast, but you have to install Boost, so installing it can be a bit more complicated. Fair is quite easy to install, but there are currently no simple input and output formats, so just NumPy arrays. But it's written in Python and only about 1,600 lines, so it's yeah, still possible to keep in your head. And now that you have multiple models, you want to compare them. And this is what we started in the OpenSCM project, but it's currently just an empty repo. So there we want to provide a unified interface. And to drive these models, you need data for input and validation, and also for visualization. So this can be global or national emissions, greenhouse gas concentrations, or temperatures. And yeah, for example, this is temperature time series for Italy. This is a more artistic visualization by Robbie Andrew, showing the seasonal change in CO2 concentrations in the past years. Or it could be an animation showing the dwindling carbon budget as we get closer to 1.5 or 2 degrees. And for all these kinds of visualization, you need ideally data in a clean format. And I was doing this quite a lot. So for example, for national emissions data, you can get them from the United Nations. And unfortunately, it comes in Excel files, so you have lots of sheets, and every year the format changes slightly. Or it can be a fixed width text file with a block for each country, also not fun to parse. Or at worst, it's a PDF file with multiple headers, and even tabular PDF can't help you anymore. So as you do this again and again, I try to put my cleaned data on GitHub, and I settled on the data package format developed by the Frictionless Data project. So I won't go into too much detail here, but I encourage you to check it out. Just to show you an example. So it's a standard to have metadata and clean data together in one file structure, and they provide specifications and tooling around this. So here I have optionally the original data, the Excel files in archive, and data are my clean data. Data package JSON contains metadata. In Makefile, I automate everything, and in scripts are the respective Python codes to clean the files. So I usually have one script to for each resource to clean it. This is what the metadata looks like. So just an excerpt. So this is describing one resource in my data package, one clean file. So there's a reference to the file, and I can also provide typing information. And then the data should just be clear, clean CSV file with only a single header line, so it's easy to read in any tool. Or even in Excel, you can open this and have no problems because it's a clean format and everything is escaped and so on. And to make it even simpler to read this, I built a little tool, Pandas Data Package Reader. So it's just a wrapper around Pandas read CSV, but it makes usage of the metadata information. So for example, if I have a type information that a column is a date, then Pandas can make use of this information. So as another example, here is a data package with entry into force status of the Paris Climate Agreement. So when and how each country ratified the Paris Climate Agreement. And I can read it. I can even read it directly from GitHub, so I don't have to download it. And this is just one line. So Afghanistan, for example, ratified the Paris Agreement in 2017. And then I can filter for countries which have not ratified. I also rename a column because I want to combine it with another data set. And thanks to GeoPandas, it's then now quite easy. So I load a global map with countries from GeoPandas. And then I here merge the two. And then I can just plot it in color the countries by ratification status. And then with just 5 lines, because I had the data already cleaned up, I can make a map of the countries who have not yet ratified the Paris Climate Agreement. So you can see Russia, for example, has not yet ratified, and a couple of probably oil-producing countries in the Middle East. Of course, there are a few more lines to clean this up, but for first picture, it's only like 4 or 5 lines of code. And all the data package that I made I try to put online on GitHub, and I also started a little web page where there are also example notebooks and binding notebooks so that I and others can easily play with the data if some question comes up. It's on openclimatedata.net. And with that, thank you, and yeah, check out these projects and make your own visualizations.
Questions?
Hi, thanks very much for the talk and for your effort in making things well organized and stuff. For the folder structure, for example, did you draw from specific templates already? And did you also spread, is it like reused in other projects that you know of, please?
So this is basically just what I copied from the, where is it? From the data package specification. So they started the frictionless data project from the Open Knowledge Foundation. They started this. They have many core data sets which follow the same structure, and I try to stick to it. So there are always minor differences, but yeah, that's what helped me, so I don't have to come up with a new format.
It's also a question about the data package. Has it an ability to have versions? Because I can imagine that like the data about the climate agreement, that it changes constantly.
Yeah. So for this data set, I just updated on GitHub. So you have the GitHub commits, but there's also fields for having versions included and DOIs or other references. So this is also part of the specifications.
Any more questions? Thank you.
Yeah. Okay. I don't know.
Yeah.
We can try. It's a Linux one, but we can try. Should work.
Mint root directory. Yeah. Oh yeah, this one. Okay.
Next talk would be remapping or regridding between spherical grids for Earth modeling.
Oh, thank you much. Hello everyone, my name is Kywan Kim. I'm from Korea Institute of Atmospheric Precision Systems. The title of my presentation is Remapping or Regridding between Spherical Grids for Earth Modeling. The presentation is as follows. I will introduce the remapping method on the sphere, a new neighborhood search algorithm, and a new remapping toolkit in order. Earth system modeling consists of atmosphere, ocean, land, sea ice, and other component models. And each component often uses a different grid system. For example, the most popular random grid, cube-sphere grid with no singular poles, and tripole random grid that moves the poles to the continent. If I want to combine an atmospheric model using the cube-sphere grid and an ocean model using the tripole random grid, mutual remapping between the different grid systems should be required. Remapping is also required for preparing the ancillary data, initial field generation, post-processing, observation data processing, and so on. So I currently I use 6 remapping methods: nearest, bilinear, Lagrange polynomial, dominant type, set average, conservative method. The nearest method is to find the source grid point closest to the target point, and then copy that value from the source to the target. The left picture shows the remapping from the blue color grid to the red color grid. So, copy the value of the nearest blue point to the red point. Bilinear interpolation, which is a popular method, is used when the source grid is logically rectangular. As shown in the figure, find the rectangular for points that enclose the target point and multiply the weights given by the area ratio. Lagrange polynomial interpolation is only available when the source grid is the Q-sphere grid. The remap accuracy depends on the number of quadrature points of the Q-sphere grid. When there are 4 quadrature points on one side as shown in the figure, so that the accuracy is guaranteed. The following 3 remapping methods use spherical Voronoi diagrams. The Voronoi diagram consists of perpendicular bisectors with neighboring points. For example, the Voronoi diagram of the left cubed sphere grid is shown at right. The dominant type method finds the dominant type of the source grid points contained in the Voronoi polygon of the target grid, or calculate the ratio of the source types. The set average method calculates the average value of the source values contained in the Voronoi polygon of the target grid. This method is suitable for remapping of masked data used in Arsham model. Finally, the conservative method uses the area ratio of the source grid points contained in the Voronoi polygon of the target grid. This method is suitable for remapping of physical quantities such as flux or mass, which should be conserved after remapping. Each of these methods has different properties, but can be expressed in the same way as the remap matrix. As shown in the figure, the target point number 4 is obtained by multiplying the source grid points number 2, 3, 5, and 7 by the appropriate weights. This association can be expressed in the form of a matrix vector multiplication. Since the remap matrix is a sparse matrix, it can be expressed simply as 2 arrays of source address and weights for computational efficiency. It is very important to find the source grid points near the target point in all remapping methods. In the case of a structured grid, such as the random grid, it is relatively easy to find neighboring points. However, in the case of an irregular grid, it is not easy to find neighboring points. We have developed a new search algorithm that can quickly find neighboring points, even on randomly distributed points on the sphere. It was developed by combining the linked cell mapping and the Q-sphere elements. The key idea is to map the grid points to be used for search to the Q-sphere elements as shown in the figure. First, prepare 2 integer type arrays named cube links and grid links. The cube link array is three-dimensional, and the grid link array is one-dimensional. For example, let's map 3 points to the red colored element in the figure. The integer coordinates of the red colored element are 8, 786. And those of the 3 grid points are 1067, 1068, and 1069. As shown on the left on the figure, it starts from cube link array and links grid points index sequentially. The mapping is done is simple. When searching for a neighboring point, it searches only the element containing the target point and its neighboring elements. If the target point is a red colored X point in the figure, the nearby source point can be found by searching for the yellow and cyan colored elements only. This is the result of measuring the search time while increasing the number of n grid points up to 10 million. If all points are compared with each other, it takes time proportional to n squared, as black line in the figure. But the proposed method theoretically takes time proportional to n times log n as blue line. The actual measured time was proportional to n as red line, which was relatively small. Now, let's take a look at a new remap toolkit that implements the above remapping methods. The name Kim is the name of the global atmospheric model project developed in my company. The main features of the remap toolkit as follows. It supports remapping between arbitrary spherical grids, even randomly distributed points on the sphere. And it supports both Fortran and Python interfaces. Unit tests for almost all functions are being performed. It includes an automated just-in-time build system. Lastly, OpenMP was applied to improve the speed. Here is the directory structure of the remap toolkit. The source directory contains Fortran codes, and the pylib directory contains Python wrappers of those Fortran codes. There are unit tests in the test directory, and the build .py in the PyUtils directory performs automated compile, link, and wrapping. There are shared utilities that perform sorting, matrix inversion, quadrature points generation, and coordinate transformations. The search tools are the implementation of the new search algorithm described above. The final category is an implementation of the 6th remapping method. I made Python wrappers using the sheet types and NumPy sheet types lib. This slide shows a sample example. The Fortran sample module has a subroutine named mySub, and each argument types are integer, single from, one-dimensional array, and two-dimensional array. Compile with Fortran as a dynamic shared library file. Load the compile file using NumPy sheet types lib in the Python wrapper. Specify the data types of the mySub subroutine and each argument as shown in the right code. Finally, when the function is called, the arguments should be casted to proper sheet types. With the same way as this example, I made Python wrappers for Fortran subroutines in the remapping toolkit. For example, a Fortran module named remap bilinear has 3 subroutines defined as cube to grid, random to grid, and grid to grid. There is a one-to-one correspondence between the same named Python wrapper file and each unit test. The user script uses the Python wrapper class as shown in the code below. We are doing test automation using PyTest. There are currently 137 unit tests. As you know, the word test makes me happy every day. With the build.json file in the source directory, I can control the compile options. When a Python module is first used, the Fortran code is compiled and linking automatically. If the Fortran code is modified, it is also automatically checked and compiled again. Of course, it can be compiled manually as shown below. This Python script is a sample to perform a remapping using the bilinear method. The required information is only random coordinates of the source and target grid points. The process is completed by passing the generated source address and weights to the remapper. Let me summarize. We have developed a new remap toolkit that performs remapping between any spherical grids. And this toolkit provides both Fortran and Python interfaces. This toolkit allows you to perform various remapping methods on the sphere with only a few lines of Python script. Unfortunately, due to my company's license policy, I have not released the code in public yet. If you need the source code, please send email to me. Thank you so much for your attention.
Questions?
Hi, maybe I missed this because I walked in a little bit later, but I'm interested in your build script. Do you build, for your build script, do you have a graph of all the source modules and how they depend on each other, so that you can rebuild only the things that changed? Or how do you approach the problem of doing the building only the things that changed?
I made a Python wrapper as possible as simply. So if I change the Fortran code, I change Python wrapper and test manually. It's not made automatically, not yet. Yeah. So I'm very interested in the wrapper tool named F2X. Talked in afternoon. Yeah. So I plan to change the Python wrapper using the F2X tool. Okay.
Any more questions? Thank you.
Yeah, thank you so much. Oh, thank you very much.
You're welcome. No
Yeah.
Just
Oh yeah.
The next talk would be listening to quasars and shooting satellites with lasers.
Okay, yep, you can hear me. Hi everybody, I'm Geir Arne Gjelle. I work with the Norwegian Mapping Authority, and today I get to talk to you a little bit about what we do inside of space geodesy. My plan for this talk is to try to give you an overview of some of the things that kind of happens behind the scenes for making technologies like GPS work, or making sure your remote sensing data are good. And then towards the end, I'll also show some of the Python projects we've been working on and that we've released open source now this summer. Okay, so why are we needing the space geodesy part? So essentially, let's say we have this nice little ocean just lying there, and then it starts to rise, and we want to figure out how. So we send out a satellite to look for the ocean. However, the satellite, what it does is actually just it's measuring how far am I away from the ocean. which is not very useful information if that's all you got, right? That's by itself fairly useless. The satellite is 963 kilometers above the ocean. Who cares, really? Or similarly, say that you're somewhere you don't know where. Luckily, there are some GPS satellites, and by themselves, the GPS satellites will just tell you that they're 20,000 kilometers away from you. Again, not very useful information by itself. So we need something to tie these things together, right? And of course, it's fairly obvious we need coordinates. We need some kind of system that we can kind of reference these things to, so that we can figure out, okay, sure, the satellite is 960 kilometers over the ocean, but we know where the satellite is, so therefore we know where the ocean is, and so we kind of get this whole thing. So once we kind of have coordinates for our GPS satellites, we can use those and these distance things to triangulate and figure out exactly where we are. Is kind of what we're doing. Okay, so what I call a reference system, it's essentially what you can think of as a coordinate system, but instead of kind of drawing it like you learned in math in school, you kind of base it on reference points, and that kind of gives you then essentially an origin and those kind of things. So the kind of typical system we want to use when we're dealing with satellites is not just your latitude, longitude. We want to have an X, Y, Z system that you can kind of have your satellites fly around, and you want to put the origin at the essential, the center of the Earth, because that's what the satellites fly around, so everything becomes easier then. Okay, it's not really trivial to actually define the system, because you need to know where is the mass middle center of the Earth. And it's not like we can just dig down and find it, right? We need to somehow figure out where is the center of the Earth. Okay, and furthermore, since we're dealing with things, say for instance, when we want to measure how the ocean is rising based on satellites, well, the ocean rises maybe a centimeter or two at that level, so we need to make sure everything is really precise to be able to do this. And we want to show how this, the sea rise kind of happens over many years, so we need the system to be stable over time. So we kind of need to have very good reference systems. Okay, there's a few challenges to this. First of all, our Earth is kind of how this tectonic plates are drifting. So even though, say, we're in Europe now, and actually now we're a couple of centimeters further away from America than we were last year. So these things are kind of moving away. So that's just, even if I knew exactly my position now, my position has changed tomorrow, just by this. Then we kind of have the fact that, well, land is also rising. For instance, up in Norway, where I'm currently working, or came from, the land uplift from the last ice age is still faster in many places than the sea level rise. So if you just walk to the beach, and you can actually see the sea level is going down there, even though it is absolutely going up. And then once you have everything put together, the Earth kind of just puts an earthquake on you, and all the work you've been doing for the last 20 years is worthless. So we kind of need to find solutions to these things. And kind of the way this has been done for a long time is that you have local systems. So you kind of walk up to a hilltop, and you just look over to the next hilltop, and you can measure where things are relative to each other, and you can put in a coordinate system where you are. And it works great when you're doing local stuff. It doesn't work at all when you've got satellites, because then your local system, where you maybe don't need to take into account that America is drifting away from you, doesn't really have anything to do with those satellites. So what we do instead is that, well, we have coordinates that move. They move slowly, but for instance, if we were to put some kind of bolt or mark on this building and come back next year, we should observe that this has moved a couple of centimeters. So ever so slowly, these things will kind of move over. So we need to include in our coordinates not only x, y, z, but also time. It kind of becomes an important fourth dimension for this. Okay, so how is this actually done in practice? The basic thing is that we have something called the International Terrestrial Reference Frame. So the reference frame is kind of the reference system part. Terrestrial means it's for the Earth, and international means that it's kind of a global thing that's an international cooperation. And the way the ITRF works is that it's really just a list of coordinates of things that move. So essentially what we've been talking about now. So it will be listed, for instance, well, I put in Oslo. Oslo is actually not in the ITRF, but you have a position and you have a reference epoch, time, and then a coordinate for that exact time, and then you have a velocity on top of this, kind of saying how it moves. So the ITRF is just a list of points like this, about 1,000 points spread over the Earth. And these things then kind of implicitly define your coordinate system that you can then use to measure relative to this wherever you are and things like this. And then use essentially the ITRF coordinates for things like the GPS satellites. Okay, so how do you actually get to have this ITRF system? Well, we have, well, there's just one person. I should have apologized already for my lack of drawing skills, but hopefully this is clear. There's a person sitting somewhere on a computer, and actually there's many people in different agencies, research facilities, and so on, that are kind of doing analysis on 4 different space geodetic techniques. The one you probably heard of is GPS, or we call it GNSS, because there are many systems. So GPS is the American system, then you have Galileo in Europe, and so on. So in one word, we call them GNSS. But there's also something called very long baseline interferometry. I'll say a few more words about that soon, but that thing over there is a quasar. It's much farther away. It's typically billions of light years away. And the cool thing with having stuff very far away is that it appears to be fixed for you. So whatever those things are doing over there, we don't care. They're so far away, it seems like they're just a point. And using this, we can just actually figure out how is the Earth tumbling through space. So we use this as kind of fixed points to orient the Earth. Then we have something called satellite laser ranging. I'll also say a few more words about that. In practice, we're then just shooting at satellites with lasers and measuring how much time the laser takes to return to us. So they kind of have these reflective cubes on them, and then we can measure this time, and that gives us an idea of where the satellites are. Then we have the GNSS systems. So as I said, GPS, Galileo. In Russia, they have GLONASS. In China, they have Beidou, and so on. There's many of these. And the 4th technique is something called DORIS, which is a French system. It uses the Doppler effect, and it's kind of like GPS in reverse. So with GPS, you have satellites that have some known position that you can kind of orient yourself and figure out where you are. The DORIS system has several of these beacons spread around the Earth, and they're kind of sending out these frequencies that the satellites are listening to, so the satellites can orient themselves. So it's kind of also then to figure out where are satellites. So that's kind of coming back to the remote sensing problem. Okay, so a few more challenges. I listed a few of them. Of course, there's the obvious one, which I haven't really touched on, but the Earth is rotating. So it's kind of just going around like this. And that means that if we're kind of having our coordinate system fixed towards these quasars, for instance, the point would definitely not be still, right? I would run around like crazy. So, of course, what we do, what you kind of know, is that you have the Greenwich meridian, things like this. So you kind of fix the reference system to the Earth. So you kind of rotate the system as the Earth is spinning. So that's fairly simple. However, the Earth is actually not simply rotating nicely. It kind of wobbles around, almost like a drunk dude. So it will kind of be, whoa, whoa, whoa. And the problem with this is, of course, that when we're doing this, the satellites don't realize that we're kind of wobbling around like this. They're kind of spinning around thinking that, oh, nice little Earth down there. So we need to actually connect what the satellites are, their positions, using something we call the Earth orientation parameters. So kind of describing a little bit how we're wobbling. And these things need to be updated essentially continuously. So if we were to stop updating these things within days, weeks, months, the GPS system would be off by hundreds of meters. So we kind of need to keep up these things. Okay, a little bit more detail just about a few of these things, because I've been working with this now for like 5 years. I'm a mathematician by training, and I'm still kind of thinking it's very cool what these people have come up with. So I was talking about how we need to figure out things down to the millimeter, centimeter level. And somehow we're doing this by listening to stuff that's billions of light years away. And billions of light years is much longer than what it sounds like even. It's ridiculously far away, right? What happens is that we'll have several of these big antennas. They're not quite to scale, but think they will be like 15, 20 meter antennas or things like this. That are just listening to essentially, think of it as random noise coming from these quasars, and we have them kind of situated around. Typically we think of them as pairs, but you'll have several of them kind of listening to the same radio source. And because things are so far away, you can think of the signal coming in as essentially parallel. And then one of your antennas will first hear the signal, and then the other one will hear it a little bit later. And you can measure this time delay. And once you know the time delay, and then you kind of know which angle you're pointing at, that means that you can calculate the baseline between them. And you can have things that are then separated by 10,000 kilometers on Earth and figure out how far they are apart from each other down to the centimeter level. So this kind of gives you observations that you can then use to figure out, okay, how is the Earth actually spinning around? So what we have then is, okay, I can calculate this baseline. And if I do this, say, today, and I have a priori estimate of where my station is. For instance, I have the ITRF. So I kind of know where it should be. I know I can calculate how long should this baseline be. And I know, well, I have a guess at how much the Earth is wobbling. Well, then I can look at what I observe and how my model is looking, and I can use these things to then estimate, okay, it seems like I'm off a little bit. If I wobble a little bit differently, then my model fits better, and I can use that in estimate for the current wobble. And these kind of things are actually done daily to update things like the GPS coordinates. And then everybody's happy. Okay, and then a few words about how the SLR system works. So essentially what you have then is that you have kind of this laser station that kind of sends out a laser, and then you have satellites. So some of the GPS satellites have these, but there are also dedicated SLR satellites that are just covered with these reflector things. So when you kind of shoot laser at them, the laser beam comes straight back at you. And then you can kind of measure when the beam comes back here, and that gives you, again, a time interval. So that's typically what we do. We measure time somehow, and that gets translated to distances and positions. And the measured time interval, of course, these are lasers, so you can then calculate what's the distance. And that gives you a fairly okay way to then figure out where's the actual orbit. You kind of need to go from the distance to positions, but that's doable. And there's kind of two applications of this. One is using these spherical, extremely heavy satellites. So this satellite is probably, I tried to draw one called Lagias, which was launched into space in the 70s. It's about yay big or something, 60 centimeter diameter, and it weighs something like 400 kilos. It's ridiculous. And of course, if you know anything about space, when you want to shoot stuff into space, you want it to be light. So why would you take this thing and try to get it into space. Well, once you get it out there, it's extremely stable. So this is a totally passive satellite. It has no engines or anything. It's just essentially a piece of rock, and it kind of flies around. And I think NASA said it will probably be flying around there for 1 million years or something like this. So that means that we actually have a very stable satellite orbit, and we can use then our lasers to shoot at this thing, and that gives us actually a way to calculate the position of the station, because now we know where the satellite is, and shooting at it, we figure out where the stations are. So this gives us a way to use SLR to actually find our station position to actually help create the ITRF. So that's one of the ways that you actually get your reference system, and this is the main way that you actually figure out where is the center of the Earth. Well, I have this extremely heavy thing that flies around the center of the Earth, and observing it gives me a way to figure out where is the center of the Earth. Okay, once I kind of know where my station is, I can then turn stuff around and use this to also start shooting at some of these altimetry satellites, for instance. Because that gives me now a very precise way to figure out where are these altimetry satellites. So I can get very good coordinates for these things, and then suddenly this number that we had in the beginning, it's 963 kilometers above sea level, makes sense. It's suddenly a useful number, right? Because I have the coordinates there, and I can figure out, okay, then my sea level has actually been rising a centimeter or something since last year. Okay, so far I haven't really said anything about Python, so I should probably do that as well. So this is some background. Hopefully you get some idea about the complexity of what's happening, and unless you're kind of into these things, you probably haven't really heard about all the stuff that's actually happening to get the magic of GPS into your phone. This is just a tiny part that I'm kind of a little bit knowledgeable of. Of course, the whole system is much more complicated than this as well. But what we've been doing is developing a software that we call the WHERE, since that's kind of the question that we're trying to answer. And what WHERE does is that we essentially take all these things. We have the SLR data, DORS, VLBI data, GNSS, and things like this, and we try to analyze time series from these things, and then actually come up with these estimates. So we could do these Earth orientation parameter estimates. We could try to figure out the wobble. We could try to figure out station positions and things like this. So where's the software where you can analyze VLBI, SLR, and these GNSS data and contribute to the ITRF? So I guess I didn't say so, but the ITRF is constantly updated, where constantly means probably about every 5 years or so. So there was the latest ITRF was 2014. There'll probably be a new one in 2020. So how is WHERE built? So originally it was a part of a Fortran project, and a lot of the space geodetic stuff was kind of built up in the 70s. So there's tons of Fortran lying around in all kinds of softwares. So this kind of gave us a chance to, okay, let's try to go mostly Python instead. And we have now WHERE is essentially, it's mainly NumPy stuff working fine. There's some conventional models, so there's tons of physics behind all of this. And we don't want to mess with physical models that kind of been around, so those are implemented already and well tested in Fortran. So we just wrap them using F2Py, which works very nicely. We can then call directly into them. The one thing we usually throw on top of there is some kind of vectorized wrapper, because the Fortran models that they have made doesn't support vectorized stuff. And then we've been using a little bit of Python. For most of the part, we haven't really needed it, but when we want to actually figure out satellite positions, then you kind of need to integrate up your position, so you kind of do things stepwise, and then you can't take advantage of the vectorized stuff. So then Python was a great help. It's open source, so it's online. You can go have a look at it. Although, as you probably have figured out, this is a fairly niche thing. So the number of people actually needing and using this is probably less than the number of people in this room, I guess. And I guess none of you are here, but there's still some interesting stuff inside of this. So some experiences, so these are just some screenshots from the analysis that we're doing. Some experiences, well, first of all, working with Python has been fantastic. We kind of sat there pulling our hairs a little bit over the whole Fortran stuff, and then each and every one of you who actually contribute to the Python data science stack and these things have been tremendously helpful. Performance-wise, as I mentioned, we kind of had some of this software already in Fortran. Our current Python stuff is about 10 times faster than that Fortran code. And essentially the experience, I guess, is that writing decent Python is faster than writing non-optimal Fortran code. And our code base is also at least 10 times smaller, so it's much easier to actually keep track of what's happening. That said, there are other softwares doing similar stuff in Fortran that are 10 times faster than us again, so there's still some plot to go. I also mentioned Python can help a lot. So, for instance, for this orbit integration of satellites, in the pure NumPy version of that code, took about 5 hours to integrate up 1 week of a satellite orbit. Now, after going through Python and some other optimizations, we're down to a few minutes. So it's kind of a massive speed up there. Of course, that's because we couldn't take advantage of what NumPy is good at. So by Python, you actually get the C-speed loops. OK, a little bit more helpful maybe than the Where software is that we're also taking out all the things that we see can be reusable from Where and putting them into its own library. We call it Midgard, since that's kind of partly named for this old snake surrounding the Earth, so you kind of have the whole geodesy Python part. And the idea there is that you'll find, this is still very fresh. You can pip install it, but the contents is essentially close to nothing. But what we are putting in there is some of these containers that we have for coordinates that move over time and things like this. You have, we've been using quite a bit from AstroPy, has a very nice time module for dealing with very detailed time stuff that we need. And then there's several of these kind of weird geodetic file formats. For instance, if you actually want to look at the raw data from GPS, you use something called the RINEX format, Receiver Independent Exchange format. That's kind of, it's used there, but it's not, you can't say pandas from RINEX. So we have some of these kind of things available. So if you kind of ever need very precise kind of what we call geodetic level positioning things, then this might be helpful. OK, so I'll stop there. And I guess now finally, this picture is actually of actual VLBI antennas. I think here you can see a few people, so you can kind of see the scale of these. These are the new observatory that we've been building in Norway up in Svalbard, so it's at 79 degrees north. And these are fairly small VLBI antennas. They're 13-meter radius. And then we are currently building right there satellite laser thing that should be able to shoot stuff. OK, that's it. Thank you.
Questions?
Hi, thank you for your talk. I have a, I think, more general question. So you know how you say that you use the positions of the various observatories to kind of determine where the satellites are and kind of vice versa. Is this like an iterative process, or could you start from just like choosing some random places on Earth, put your observatories there without knowing anything and kind of working out where they are? Or do you need some prior knowledge to like start the whole system?
Right. Yeah, so it's kind of based on, as you say, we use the a priori information quite heavily. And when you build a new place, you kind of suffer for a while that we don't have good coordinates for it. But then you use things like, well, you can use the GPS to actually figure out where is the system, and you do what's called local ties to kind of tie together. So it's probably not really visible in this, but there's a bunch of actually GPS antennas scattered around there to kind of both figure out where it is and make sure it doesn't start moving, because we want these things to be extremely stable. So you kind of start to get this into place, you kind of want to get a fairly good guess at where you are, and then you kind of improve on it.
What kind of models are used to estimate the wobble that you were mentioning before?
So what's typically used by most people is least squares kind of regression things. In our software, we've implemented using Kalman filters instead.
So you mentioned about tracking the satellites and things, and there's quite a lot of radar going on in these, well, in tracking satellites in general. Yeah. But you specifically talked about the lasers a lot. Presumably they're much more accurate, or like, can you talk a little bit about the difference?
Yes. So, yeah. So for satellites where you really want to have the precise orbit, let's see. Do I have a decent overview of this? Let's see. So where you want to have really precise orbits, so as you say, you can track satellites with, I guess, several techniques now. But when you want to go down to, okay, I need to get this down to centimeter level, there's essentially two techniques. It's the SLR and the DORIS that gives you that really high precision. So the DORIS is used on, for instance, the Sentinel satellites that was mentioned in an earlier talk today, to get really good orbits for this. And also, many of those kind of satellites will have SLR reflectors on them. I guess the SLR is slightly better than DORIS in theory, but the DORIS, you kind of, once you put the DORIS receiver in your satellite, you actually get your positions. While the SLR, you're dependent on somebody actually shooting at your satellite. So it's, so yeah, if you want to get really, really good orbits, then you kind of need to do this. But it's a little bit like, I mean, here we're talking about I want to have my GPS position down to the centimeter. Of course, when we're going out to meet at some bar later tonight, we don't need that. If we can find within 5 meters of the bar, we'd probably all make it to the same bar, right? So this is not that useful for us. But for more these professional applications where you're doing things like, well, the remote sensing climate things, then you would need these.
Thanks for the nice talk and the great images. Have you had to build any code to deal with general relativity effects for the distance calculations?
Yes. We need to take relativity into account, I guess. I didn't say too much about this, but there's tons of interesting physics going on here. And I guess that was kind of my most interesting experience coming from mathematics, is that I was kind of happy that the Earth was a sphere, and I would typically think of it as a sphere with radius 1 even. It's kind of more than enough. And then you kind of, okay, I can agree that it should be an ellipsoid, but it's not even that, right? It's this bumpy little thing that even goes up and down. So one of the cool little things that I learned is that, well, we heard about tidal water, that kind of the ocean is rising. The Earth is rising up and down as well, like 30 centimeters probably throughout the day. So you kind of, but you don't see it because it happens more or less uniformly. But from the satellite, you notice these things. So we need to take those kind of things into account. And as you say, relativity is fairly important when you want to get down to these levels.
So are those bits included in the open source package?
Yes, there should be at least some of the methods there. Of course, many of these things are some smart physicist figured out some time ago, and then there's just an equation that you don't really see what's happening. But yeah, there's a few things where you can explicitly, you can search for relativity and get some hits inside of it.
Thanks.
Sure.
Thank you.
Thank you. Sorry. No, I'll just take my. Well, leave this one.